We have independent variable, we have shift operator that substitutes x plus 1 instead of x into arbitrary function or expression. And, well, if we look at rational functions, so all rational functions which are considered here are already reduced numerator-denominator, and degree of numerator is less than degree of denominator, so they are proper. And the important notion that is relevant for indefinite summation is notion of dispersion of rational function, introduced by Sergei Abramov in 1971, 40 years ago. It is the maximal integer distance between roots of the denominator. That's what we are going to see and touch. Well, n all over the places here is degree of denominator of a proper rational function. And problem of indefinite summation in general is, given a closed form expression, we do not specify what class expression comes from. To find the closed form expression g such that if we take a first difference of g, we will get f. That's the definition. So if g of x is found, that solves this first order recurrence, then we write indefinite sum of f is equal to g. Well, our butter is butterish, so we can rewrite it f. I rewrite this f is equal to e minus 1 applied to g of x. Then we take sum on both sides, and since summation and differencing cancels each other, again, this is kind of cheating we see all the time in summation. So butter is butterish, something is summable means that, well, it's the same as with integration. To find to find a function such that when you differentiate it, you get integrand. It's very similar thing. Well, this part is important here because we will actually use this trick for accelerating the algorithms for indefinite summation. So that's the part where I hope, well, I can just hope that only this part is boring. This is definition, okay? So function is f is summable if we can find solution of this first order recurrence. And then we write indefinite sum of f.
For people who came late, remind them, even though you shouldn't come late, if you came late, the E of
E
of
is
X,
shift operator. E is shift with respect to x. So E applied to g of x is g of x plus 1. So then e minus 1 applied to g of x is g of x plus 1 minus g of x. And if this happens to be our summand, then g is sum, indefinite sum. The same as with integration. Replace this by integral sign and differencing by differentiation. The same thing. Well, closed form expression, now it's time to actually speak what kind of expressions we have in mind. We are looking for closed form expression. G, what does it mean? What do we actually want? We have problem, summation problem. Sigma x of f of x. We want to know what is on the right. If we just want to get rid of this indefinite summation sign, then there is very easy trick found applied to different summation problems, starting with Igorachev's books and even earlier. So you take arbitrary expression, write it using exponential form of Fourier transform, write it in this form, then apply summation on both sides, summation in n. Well, justify change of order of summation and integration. You got very simple geometric summation with respect to n. Everybody knows what is geometric sum is. So it is here. So we got universal summation formula, works for every expression. Every expression. I got rid of summation sign. Well, what I earned is double integral, but who cares? It doesn't have summation inside, right? So, well, this is cheating. And actually okay, let me, actually this trick is done many times in Yegorachev's book, and look, when you do summation under integral sign, it is usually geometric summation, or as we will see later, quasi-rational summation. And then it takes nothing to do this sum, and then everything is, well, you introduce singularity here, but what is your function here? If cancellation happens here, then you can write closed formula. But we are not going to exercise this, because this is cheating. This is just example of universal formula that you can find the papers that actually do exercise it without, and then write result without explanation how actually integral was evaluated. And you can use any pair of integral transforms, direct and reverse transform, in order to cheat on summation. We are not going to cheat on summation, so we are going to seriously discuss this indefinite summation problem. So given closed form expression, I would like to find expression in the same class as my input for indefinite sum. And well, we know that for polynomials this problem, polynomial is always summable. Well, the question is, and actually a lot of content of today's presentation comes from my personal unsatisfaction with absence of progress. Progress in terms of performance of the algorithms for indefinite summation for many years. So, like in 1977, Gosper published his indefinite summation of hypergeometric term, and it is used.
1978.
1977, first paper. Yeah, I have two papers. Remember, we did discuss, there are two papers by Gosper, one in Maxima Proceedings, which is unreadable and which doesn't have an algorithm, and then improved one in Transactions of Academy. Short, nice paper. So probably time to switch to Maple. And to, is it Maple? Yeah, it is. Okay, so here is instance of hypergeometric summation. So class of functions to be considered as proper hypergeometric in X. Well, there is only one X factorial, so if you take, well, I'm not going to go into definition of hypergeometric term. What does it mean? Well, important step in Gosper algorithm, first step is to take term shifted by 1 divided by itself. This is rational function, which is known to be if input is hypergeometric term, then this ratio is rational function, which is known as rational certificate. Well, we write it in special form, Gosper-Pitkovshik form. Here is Gosper-Pitkovshik form for this particular input. It has constant 1 and polynomials second degree, linear, and one of, I believe, 200 or 201. Well, but this is step of Gosper algorithm, so we got this.
But this is an artificial example to show how bad it is. It's not a random example, it's a cooked example to make it look bad.
Well, what I'm trying to say is that this is typical. When this rational certificate has large dispersion, like in this case, integer distance between roots and denominator is 201, then the Gosper algorithm will be exactly like this, because Gosper-Petkovchuk form will fill all the gaps. X plus 4, x plus 5, x plus will get this polynomial P will become saturated, filled in, all gaps filled in. So we have this equation, and now we are happy because we reduce it to linear algebra. We have equation, Gosper equation, made from these pieces, and well, everything is now reduced to linear algebra because it is first order difference equation with known right hand side, known coefficients. We can get degree bound, plug it in, solve linear algebra, 201 by 201, and we will get the result. Okay, so now, of course, if I factor this result, look what is in my result. But this is not last step. So now I take this solution and I plug it in. I take this solution, if it exists, P, I put R of x minus 1, and I multiply by my input term. And this will be answer to hypergeometric summation problem. So I do this. And when I normalize it, of course, everything cancels. All of terms, almost all of them do cancel here. And I got nice and short. Well, that's what is. As you see, now if I multiply it by term, I got this result. Well, which is exactly the same as Maple returns. So I did it just step by step. That's what Maple does here.
How many seconds does it take to do sum?
We will see seconds. Yeah, we will see seconds. So, of course, unsatisfaction, reasons for unsatisfaction is right here. You see that in many cases, whenever your right-hand side of Gosper equation is saturated polynomial, then this cancellation will happen. It means that dispersion, which was large here, 201 distance between roots, integer distance between roots, the running time of Gosper algorithm essentially depends on dispersion. Also, the result does not depend on dispersion. And but somehow for years, everyone was happy, right? Because, well,
it was nice
we reduced.
It was nice of you to make it x plus 200. To make it x plus 2 million.
Yeah. Well, but then we would. Yeah. Well, I tried to be nice. Yeah. But second reason is also that for many years also people did apply Gosper algorithm to actually smaller classes of function. Well, why not? You can do the same. Rational function is hypergeometric because certificate, if you shift it, if you take rational input, you compute rational certificate, shift it and divide by itself. And then, of course, you can build Gosper equation, again, polynomial rational function, large dispersion here, polynomial is saturated. We solve it. Well, and of course, when we plug it back in, everything cancels. So output is small. But everyone is happy because we can reduce it, right? We reduce to linear algebra. We don't need anything else. You want to sum rational function, run Gosper algorithm. Well, to follow this logic, why don't you? Oh, this was quasi-rational, sorry. Did I show? Yes, this was quasi-rational, which actually makes sense. Quasi-rational summation currently is quasi-rational. It is rational function times lambda to the x, 5 in this case. Quasi-rational summation is done in Maple. There is no other way just to call Gosper algorithm, because it is not rational, so you cannot call fast rational summation algorithm. It's hypergeometric, but you can repeat the same for rational and everything will be the same. Well, why don't, honestly speaking, we can apply Gosper algorithm to polynomial input and it should work, right? Because polynomial is hypergeometric. So we take polynomial, make it just a little bit, I will test something. We take polynomial, we compute rational certificate, we build Gosper-Pitkovchuk form. Well, now polynomial is not that large degree. We form this equation. Well, if you look what we formed, we actually formed exactly problem of summation of polynomial. Input polynomial is on the right hand side, and we are looking for solution of first order recurrence. Of course, it is solved. Well, then we need to substitute it solution into this form, and after normalization, we will get the same output that Maple returns without using Gosper equation. Well, so it looks like Gosper algorithm solves everything, so we just, stop now and I answer questions. After I started to look at this, so what is wrong with, with quasi-rational summation? What is wrong with Gosper? Of course, the goal is to try to produce the same result. The function is summable. We want to produce this sum, but we don't want to have these intermediate expressions well, and then everything cancels, because this is just waste of running time. So I'm, by education, I'm from computer science, and this is computer science point of view. I just was lucky 34 years ago that my supervisor I got for my first research project was Sergei Abramov, who is famous for results in summation, but otherwise I would never touch those summation problems. And this community who does summation, it's small club. Like I'm glad actually to be in headquarters of creative telescoping tonight and to speak to great creative telescoper, my friend Professor Zeilberger. And when I started to review actually what is going on, do you think that polynomial summation is fast enough in Maple? Like how does Maple or any other system sums polynomial? Well, from those examples we know what Gosper algorithm does. It reduces everything to linear algebra. It has, for polynomial, it has this equation. It will set, well, degree bounds are easy. Here it will set up linear algebra. Where is, here is equation. So degree bound is 5 in this case. Plug in unknown coefficients, degree 5 polynomial here. Simplify, got linear system, 5 by 6 by 6, solve it. If it's solvable, then, well, for polynomial, it's always solvable. So linear algebra. So what I'm going to show now, I'm going to ask a question. What is this? This Turing machine, obviously, right? It's programmed for Turing machine. Okay. What is this? This is piece of Maple code called Zam from Zima or Zeilberger way to Zam. I don't know, Zam. This is programmed to sum polynomials. This is shortest summation is simpler problem than multiplication. To find the definite sum of polynomial, it is easier than to multiply two polynomials. It is constant time algorithm here. This, well, of course it is cheating. There is trick here. Polynomials I'm looking at are given in normalized foreign factorial basis. So this is, well, which is what? Which is x minus 1, x minus 2, x minus 0 plus 1, or factorial. If we, instead of x to the I, if we take this basis, so we are given polynomial. Well, we used to have this one, but we have written it in that basis, foreign factorial basis. Then summation is trivial. You just insert 0 in front. That's it. Hmm?
Yeah, it's just.
Yeah, you just insert 0 in front. It's constant time. If my Turing machine, if my input, if head is under leftmost symbol, under here it's constant time job. To remove this, to replace it by comma, and then to write 0, and then to write bracket and stop.
Like integrating polynomials with the usual basis.
Right.
Yeah. Well, integrating polynomial with usual basis is not constant time, it's linear time. You have to do it term by term. No?
Why? By using the same data structure? But if you normalize it with n factorial? Yeah, the exact same.
Well, this is constant time.
Yeah.
And in Maple, this is constant time. Since if I don't output result, then it is constant time. So, well, if we would represent polynomials in this basis, then summation would be constant time. Well, it's not always. And it's quite possible that, where am I? Yeah. So this is toolkit. 2 lines toolkit to work with polynomials. This is to sum polynomial, and this is to take a difference. Difference is opposite. You just, if I have polynomial in foreign factorial basis, difference is just to remove this. So this is toolkit, 2 lines, show me shorter Maple code that does summation. Well, of course we need basis conversion, polynomial to foreign, then summation is trivial, and then we want to convert, well, so summation is trivial, I show you the result. And of course we want to convert back from foreign to polynomial. Well, I first thought that this is just a joke, okay? Because, yeah, well, if we had polynomials and foreign factorial basis, from the beginning, we do in this basis we can multiply polynomials, add them effectively, everything. So then summation would be as trivial as it possible. Well, it turns out actually that this is a way to improve current implementation of polynomial summation in Maple. Because change of basis, fast algorithm to change of basis has, if n is degree, then running time is n log n, something like this. How Maple currently does summation, it computes Bernoulli numbers, right? Okay, and to compute Bernoulli number n, it's quadratic time algorithm. And so you really can, like, you can accelerate polynomial summation for large degree polynomials, of course, because change of basis is known. Fast algorithm, divide and conquer change of basis, the same as multi-point evaluation of polynomial. So it's something that we can do. So now I would like to remind you that, oh, okay, so now I have to be really quick. So rational summation algorithm is 40-year-old. Gosper algorithm is a little bit younger. There is specialization of Abramov's algorithm for quasi-rational summand done by Mann. They all exhibit the same bad thing, which is unnecessary dependency on running time on size of dispersion of denominator. Abramov's algorithm has as many steps as large dispersion is. For example, if dispersion is 1 million, it will have 1 million steps. Also, answer is just 2 terms. This algorithm has unnecessary dependency on dispersion. Gosper we have seen, well, at least on some examples when everything cancels. So we want to get rid of it. And we actually succeeded to get rid completely of it in rational and quasi-rational case. And by the way, also this argument, well, you have rational summation or quasi-rational, apply Gosper algorithm, doesn't work when function is not summable. If function is not summable in class that we are looking at, then we can try to solve additive decomposition problem. The same as with integration. Say you integrate rational function, generally answer is rational part and logarithmic part. Similarly here, the rational part and non-rational part with additional property that this one, non-rational part, is simpler than original one, or as simple as possible. In case of rational function, it means exactly the same as for rational integration problem. Non-rational, just difference is that dispersion is 0 here. And additive decomposition problem, well, Gosper algorithm doesn't solve it. It says yes if it's summable or no, and goodbye. And we would like to solve if function is not summable, if there is no expression in the same class that is indefinite sums, and we would like to write it in the form summable and plus non-summable part. And non-summable part is as simple as possible. Well, for rational function, it means degree is 0. But when input is non-summable, here is my example. This one is non-summable. Dispersion is what, 10? 11? This is not summable. So here is rational part, here is non-rational part. But this answer is not unique. And for example, here is different. The same indefinite sum. Here is rational part, the non-rational part is shifted by 6. It is much simpler. Now, the same property, the same requirements are satisfied. Dispersion of non-rational part is 0, but rational part is now minimized. So then for additive decomposition, it makes sense to formulate it in such a way that we would like to decompose sum into summable and non-summable part, with this one as small as possible, dispersion is 0, and this one as small as possible. Well, and actually, I wanted to mention something that for rational summation, it is 40-year-old. Algorithm is 40-year-old. Okay, it was not known in North America until 93 or 94. Interesting question. Okay, if algorithm was not known, how did computer algebra system solve rational summation problems? How did they do it? How Wolfram did it? So let's take a look at how Wolfram would do rational summation. Wolfram Mathematica will do rational summation. Well, this is, I know for sure that they knew algorithm of Abramov already, but they did rational summation in this way. And it is, in some sense, it is more honest than to apply Gosper, reduced to linear algebra.